Hello everybody, this is Saatvik Sharma, member of Comparative Programming Group, Club of Programmers, IIT BHU. In this video I'll be talking about two very important topics in comparative programming, topological sorting and strongly connected components of a directed graph. Both of these topics are very important in comparative programming and can be used to solve a wide variety of problems. So let us start with topological sorting because it is also required in finding the strongly connected components. So suppose we are given a graph G with V vertices and E edges. We need to find a permutation or an ordering of the vertices such that for any edge E directed from U to V, U comes before V in this ordering. The only prerequisite required for topological sorting is the knowledge of DFS. So if you don't know about DFS, I would request you to please go and learn about DFS first. So given a graph G with V vertices and E edges, we need to find a topological ordering of its vertices. The first thing that we need to understand is that topological ordering exists only for directed acyclic graphs. Let me explain this with an example. Let us suppose that I take a cyclic graph like this. So here we have a cyclic graph with three vertices, 1, 2 and 3. So according to the definition of topological sort, for every edge E directed from U to V, U should come before V in the ordering. So let us say that we are talking about this edge E. So for this edge it is directed from 1 to 2, so 1 should be present before 2 in the ordering. Similarly for this edge, 2 is before 3, so 2, 3 in the topological order. But for this edge we see that it is directed from 3 to 1, so it should be that 3 should come before 1 in the ordering. But here we have a contradiction because 1 is already before 2 and 2 is already before 3. So this is not possible and topological sorting does not exist for cyclic graphs. Another important thing is that there may exist multiple topological orderings for the same graph. So let me take an example here also. Let me draw a graph. So here we have a graph with 5 vertices and we will get to the procedure of finding the topological order later, but let's suppose that I write this order as 1, 2, 3, 4 and 5. So you can check for yourself that this order is a valid topological ordering because 1 comes before 2 and for this edge 1 needs to come before 2. 2 comes before 3, for this edge 2 needs to come before 3. 1 also comes before 3 and that is true for this edge. 2 before 4 for this edge. 3 before 4 for this edge and 3 before 5 for this edge. So this is a valid topological ordering. But if I take another order which is 1, 2, 3, 5 and 4. Now as you can see that this is also a valid topological ordering. Why? Because for every edge this ordering is still valid. Since there is no edge between 4 and 5 and their order does not contradict with any of the previous edges, so we can write 4 and 5 in any order and it will still be a valid topological ordering. So what I'm trying to explain is that there may exist multiple topological orderings for the same graph. Okay, so let's move forward and find out what is the procedure for finding the topological ordering. So basically it is a simple DFS with only one extra line of code, I'll say. We can do a simple modified DFS to find the topological ordering of a directed acyclic graph. For every vertex we require that each of its descendants should be present in the ordering after the given vertex. So let's suppose that I have a vertex 1 here, vertex number 1, and it has two children, vertex number 2 and vertex number 3. So because there is an edge from 1 to 2 and from 1 to 3, I require that vertex number 1 should come before 2 and before 3 also. So because 2 and 3 are the children of 1, I require that the children of any vertex should come after the parent vertex in the topological ordering. So what we do is we take an empty vector and we run DFS starting from any arbitrary vertex. For each vertex we push it into the vector only after all of its children vertices have been processed. This way we ensure that for every vertex its position in the vector is after its children. We repeat this procedure for each unvisited vertex, and at the end we print the vector in reverse order. The obtained order is the required topological ordering. So let us run this algorithm with the same graph that I took before. Let me just quickly draw it again. This is the graph that we are taking, and let's say that I have an empty vector v here. So I start my DFS from any arbitrary vertex. Let us say that I started from vertex number 1. So I mark the vertex 1 as visited, and I move to the children of 1, which are 2 and 3. So let's say I move towards 2. So here I mark 2 as visited, and note that I don't push any vertex in the vector right now, because according to my algorithm I only push a vertex in the vector when all the children of that vertex have been processed. So now currently we are at 2 and there are still unprocessed children left for 2, which are 3 and 4. Let's say I move towards 4 and I mark 4 as visited, and now you can see that there are no more children left of 4 that are yet to be processed, that we can say that all the children of 4 have been processed. So we push 4 into the vector. Now we move back towards 2 and there are still unprocessed children left for 2, which is vertex number 3, and we mark 3 as visited. And for 3 there is vertex number 5, which is a child of 3 and it is yet to be visited. So I visit 5, mark it as visited. Now for vertex number 5 there are no more children left, so I just push it into the vector 5. I move back towards 3, and now for 3 both the children have been visited, so I push 3 into the vector. I move back towards 2, and now for 2 also all the children have been processed, so I push it into the vector. And now I move back towards vertex number 1, and now all the children have been processed, so I push 1 into the vector. So the vector I have obtained is 4, 5, 3, 2, 1, and at the end I reverse this vector. So the new order that we obtain is 1, 2, 3, 5, 4. So this is the required topological sort. So the reason why this algorithm works can be understood that we are storing the vertices based on the increasing order of their finish times of DFS. So if there is a vertex that has 2 children, so obviously the DFS of the children will end first and the DFS of the parent will end only after the DFS of its children has ended. So we always ensure that the parent child comes after the children vertex, and when we reverse the when we reverse the vector, the parent child will come before all of its children vertices, which is what we want in topological ordering. So let us look at the code of this algorithm. So first I have this DFS function which marks the current vertex as visited, and for each child, if the child is not visited, it runs DFS from that child as we do normally. And here this is the main line where we push the vertex v in a vector named answer. In the main function I've taken the input of the graph in the form of an adjacency list, and then I mark each vertex as unvisited initially. I run the DFS from every unvisited vertex, and at the end I reverse my vector and then I print my vector. So for the example I've taken the same graph which I just explained to you. Topological sort for the given graph is 1, 2, 3, 5, 4. And the complexity of this The complexity of this algorithm will be the same as that of DFS, because we are just doing a normal DFS with just one extra line of code, which is O of V plus E, where V is the number of vertices and E is the number of edges. The extra space required will be the order of V, where V is the number of vertices, to store the topological ordering. The applications of this algorithm are activity scheduling problems, and if we have to solve some system of variables which have some inequalities or some constraints between the variables, we can do these problems with topological sorting. And here I've given two practice problems where you can practice this algorithm by yourself and gain confidence in it. So now let's talk about strongly connected components of a graph. A directed graph G is said to be strongly connected if there exists a directed path between any two vertices of the graph. If the graph is not strongly connected, it can be broken up into two or more strongly connected components. The prerequisites required for strongly connected components are DFS, topological sorting, and the transpose of a graph. So what are strongly connected components? If you remember the definition of connected components in an undirected graph, you can see that the definition is basically similar to that definition only. The only difference here is that the graph is directed this time. So for connected components, we define that if for an undirected graph, each vertex is reachable from each other vertex in the graph, then that graph is said to be connected. Here also, in a directed graph, if we say that each vertex is reachable from any other vertex in that graph, that directed graph is said to be strongly connected. So that is what I've written here, that in a strongly connected component, each vertex is reachable from every other vertex in that component. Now, given a graph G with V vertices and E edges, we can find its strongly connected components using Kosaraju's algorithm. So for example, let us take a look at this graph here. It has 5 edges, it has 5 vertices, and let us consider these 3 vertices first. So for vertices 1, 2 and 3, we can see that vertex number 1 is reachable from both vertex number 2 if we follow these edges, and it is also reachable from vertex number 3. Vertex number 2 is also reachable both from vertex number 1 and from vertex number 3. Vertex number 3 is also reachable from both vertex number 1 and vertex number 2. So these 3 vertices together are said to form a strongly connected component. Now if we take these 2 vertices, number 4 and number 5, here we can see that number 5 is reachable from the other vertex in this component, which is vertex number 4, but vertex number 4 is not reachable from vertex number 5. Why? Because this edge is directed from 4 to 5, so we cannot go from 5 to 4. So these 2 vertices do not form a strongly connected component. Instead, in this graph, there are 3 strongly connected components. One is this one, and another is vertex number 5, and the third one is vertex number 4. So these circled components are the strongly connected components for this graph. So let us see about Kosaraju's algorithm. There are basically 3 steps to this algorithm. The first one is that we do a DFS for every unvisited node in the graph, and we store the vertices in a vector in increasing order of their finish times of the DFS. At the end, we reverse this vector. So if you remember, this is exactly same to what we just did for topological sorting. So let me take a new graph and show you with an example. I've taken this graph with 7 vertices, and you can see this graph. And I've also taken an empty vector V, just as we did before. So for the first step, we just do the same algorithm that I previously discussed with you. So we start my DFS with this arbitrary vertex, vertex number 1. So I mark 1 as visited, and then I move to the child of 1, which is 2. I mark 2 as visited. I move towards 3 and I mark 3 as visited. Now 1 is already visited, so I don't move there. I move towards vertex number 4. 4, I mark it as visited. Move towards 5, I mark 5 as visited. I move towards 6, I mark 6 as visited. And I now move towards vertex number 7, and I mark 7 as visited. Now for vertex number 7, there are no children available to process, so I just push vertex number 7 inside the vector. I move back towards 6, and now all the children of 6 have been processed, so I push 6. Similarly, I move back towards 5, I push 5 in the vector. I move back towards 4, all the children of 4 are done, so I push 4 in the vector. I move back towards 3, all the children of 3 are done, so I push 3. I move back towards 2, all the children of 2 are done. and finally I move towards vertex 1, and vertex 1 is also done. So this is the vector that I obtained on doing my first step of the algorithm, and as we did before, we reverse this vector, and then we obtain the order as 1, 2, 3, 4, 5, 6, 7. So this is the order that I have obtained. This is what we store in the new vector. So for the second step, we take the transpose of the graph by reversing each of the edges. So let me take the transpose of the graph now. For those of you who don't know, the transpose of a graph is basically the same graph with all the edges reversed. So as you can see, I've taken the transpose of this graph by reversing the directions of all the edges, and this is the vector that we obtained in the previous step. So for the next step, we do that for each unvisited vertex in the vector. We do a DFS starting from that vertex, and the set of vertices SV reachable from that vertex V is the strongly connected component of vertex V. So let me explain this. I take the vertices in the order that they are present in my vector, and I start a DFS if that vertex is unvisited. Now all the vertices that I reach in that DFS run are said to be the strongly connected component of that vertex. And at the end of each DFS run, I say that I have come to the end of one strongly connected component. So first I start with vertex number 1. It is unvisited, so I start my DFS from vertex number 1. I mark it as visited. Now from 1 I move towards vertex number 3. Note that I am doing my DFS on the transpose of the graph. So I move towards 3, I mark 3 as visited. Then I move towards 2, I mark 2 as visited, and I come back towards 1, and now no more children left to process, so this DFS run is complete, and I obtain the first strongly connected component as 1, 3, 2. Now we come back to the vector, and I move towards the next vertex in order, which is vertex number 2, but it is already visited, so I move ahead to vertex number 3, and vertex number 3 is already visited, so I move towards vertex number 4. I start my DFS from vertex number 4, I mark it as visited. Now I move towards vertex number 3, but 3 is already visited, so I don't process it. I move towards vertex number 6, and I mark 6 as visited. Then I move towards vertex number 5, and I mark 5 as visited. I come back towards 4, and now my DFS run is complete. So I obtain another strongly connected component as 4, 6, 5. So this is one strongly connected component, this is another strongly connected component, and now we come back to the vector. 4 is done, we move to 5, but 5 is also visited, so we move towards 6. 6 is also already visited, so we move towards the last vertex, which is vertex number 7. 7 is unvisited, so I start my DFS from vertex number 7. I mark it as visited, and now there are no more children left for 7, so I just have this strongly connected component as the individual vertex number 7. So for this graph, I am obtaining 3 strongly connected components. One is this, containing 3 vertices. The second strongly connected component is this one, also containing 3 vertices. And the third one is just this one vertex component, which is vertex number 7. So my algorithm is done, and I have obtained the strongly connected components of this graph. So the number of times we did DFS to visit all the vertices is the number of strongly connected components in the graph, which for this graph was 3. So let me explain why this algorithm works. So here I have the original graph again. Please note that I have taken the original graph, not the transpose that we just worked with. So in the original graph, if I represent my strongly connected components, I can just circle them as this. So let us take a strongly connected component and represent it by just one vertex. Let's say vertex A. So what I'm doing is I'm creating another graph just to demonstrate, and in this graph each strongly connected component of the original graph is represented by just one vertex. So this connected component is A, this connected component will be, say, vertex B, and this will be C. And now we can see that since there is an edge from vertex 3 to vertex 4, which basically means that there is an edge from this component to this component, so in this graph also there will be an edge from vertex A to vertex B. Similarly, there will also be an edge from vertex B to vertex C. So I have obtained this graph, which is called the condensed graph of the original graph. So what I do is, in the first step I sort the vertices based on the increasing order of their DFS finish times. So basically, if there is an edge from A to B, I am guaranteed that at least one vertex from the connected component A will finish its DFS after each vertex from component B has finished. Why? Because in a way, B is the child of A. So we know that in DFS the children always finish their DFS first and then the parent vertex finishes its DFS. So if there is an edge from A to B, I am guaranteed that there will be at least one vertex which will come in the vector after each vertex from B has been pushed into the vector. Similarly, we can say the same for B and C, that there will be at least one vertex from B which will come in the vector after vertex number C. Take my vector which I found in the first step. It will look somewhat like this. C will come first because it will end first, then B will come because it is the parent of C, and finally A will come. And now if you remember, at the end of the first step we reversed this vector, so what we obtain is now A, comma B, comma C. And in the second step we then took the transpose of this graph. So let me just reverse the edges here. Now this edge is directed from B to A. Also this edge is now directed from C to B. For the third step, I start my DFS in order of the vertices in the vector. I start from vertex number A. For vertex number A, I start my DFS, and now we will find that the DFS for vertex A will only traverse all the vertices present in A only, and it will not go towards B. Why? Because the edge from A to B has now been reversed and we cannot go towards B. So we will only visit these vertices which are present in A. So I get the strongly connected component A. A is done. Now we move towards B. We start the DFS from B. Again we visit all those vertices that are present in B. We cannot move towards C because the edge has been reversed, and also note that we cannot move towards A because the whole A component has already been visited. So we get only the connected component B. Finally we move towards C, and for C also all the vertices present in C will be traversed, but no other vertices will be traversed. So we finally get these connected components A, B and C, which were the connected components in the original graph. So this is just what I've explained, I've written here in the text, the condensed graph and the strongly connected components. So now let us look at the code of this algorithm. So here we require two DFS functions. The first one is similar to what we just did for topological sorting, where we have a normal DFS and then just one line here where we push the current vertex in the vector answer after all of its children have been processed. In the second DFS function, which is what we do on the transpose of the original graph, we do a normal DFS and then we just print this vertex which we are currently on. This will just ensure that we are printing the strongly connected component by printing each vertex that we travel. In the main function, I have input the graph in the form of an adjacency list. I mark each vertex as unvisited. I do a DFS, the first DFS function, and then I reverse my answer vector as we did before. Now for obtaining the transpose of the graph, it can be done easily by making another adjacency list, and for each edge present in the original adjacency list, I just push the reverse of that edge in the second adjacency list. For example, if there is an edge from, say, vertex U to vertex V in the original list, I will push vertex U in the adjacency list of vertex V in the second adjacency list. And now for the second time I run DFS for each unvisited vertex. You can see in the input I provide the same graph which I just explained to you, this one, and in the output I'm getting these three strongly connected components as I just explained. So the complexity of this algorithm is O of V plus C because it consists of two DFS runs, each of which requires O of V plus C time. Obtaining the transpose of this graph can be also done in O of V plus C time, provided that the graph is stored as an adjacency list. The space complexity is again O of V for storing the vertices in a vector. Here I have some practice problems for you to practice this algorithm. So thank you for watching, and the links for both the documents and the codes that I have used can be found in the video description. Please like this video, comment if you have any doubts, and subscribe to our channel. And thank you for watching.